This video is about trigonometric ratios and special triangles. Begin as always by reading carefully through the textbook and taking notes, but now consider the following highlights for this topic. We'll begin with trigonometric ratios. Now, these make sense only in the context of a right triangle. So I'm going to draw a right triangle to help us understand a visual setup for what's happening with these ratios. A right triangle is simply a triangle that has a right angle in it. So we'll just draw one such triangle. Hand drawn is never perfect, but we'll do our best. And usually a right angle is labeled with a square little box in the angle corner. Okay, so of course a right angle is 90 degrees. We've been working with those kinds of things already, but I'm just going to put the label for the right angle in the corner of the triangle. That is the right angle. Now, once we do that, we're also going to label one of the other angles in this triangle as theta, just to give it a name. And it does not matter which of the other angles we label. I'm just going to pick on one of them. You could as well just pick the other. It doesn't really matter. But the way we label that angle theta will determine which side of the triangle is labeled which. So here's what I mean. Across from the right angle, you will always have, no matter which way the triangle is oriented or spun around or flipped upside down, across from the right angle, so if you were standing on the right angle and looking across the triangle at the side that's not touching the right angle, that would be the hypotenuse, and it's that way every time. Hypotenuse is always across from the right angle because the right angle is the biggest angle, and the hypotenuse will be the biggest side. Now, if you look at where I've labeled theta, which is, of course, one of the other angles, those other angles must be less than 90 degrees in order for this to be a triangle, which means they're called acute angles. So I've just picked on one of them to label it as theta. And if I look across the triangle, imagine I'm standing on theta in that corner, looking across to the side that's not touching theta. That side is always the opposite side. And so there we have some labels showing up on this triangle. Then the only other side shown, the one that would be next to theta but not labeled, would be the adjacent side. Adjacent is a word that simply means next to or touching, and so adjacent to angle theta or touching it, you have the adjacent side. And you'll notice that that would all change if I change where theta is. Okay, so for example, we'll see examples of this, but if I changed and put theta in the opposite angle corner, so the other acute angle that's not the right angle, then that would change not the hypotenuse, because that's always across from the right angle, but that would change where the opposite and adjacent are. In other words, you would switch those if you switch where theta is labeled. So we'll get more examples that I think will get us comfortable with that, but for now we're just giving a basic setup so that we can define our trigonometric ratios. Now, in the way that I've labeled this triangle, the following is true. So the sine of theta is equal to the opposite over the hypotenuse. So now think this carefully here. Opposite is a side length of the triangle. It's one of the sides of the triangle that gets labeled according to wherever theta is. And that side of the triangle has a length or a measure, right? That's what we're talking about as the opposite. The hypotenuse for the denominator in this case is also a side length of the triangle. Of course, it's the length of the hypotenuse of the triangle, which is always across from the right angle. So we're seeing that really this trigonometric ratio is a fraction or a ratio of side lengths of the triangle, and those side lengths are labeled by these words. For sine, it's opposite over hypotenuse. All right, if we carry through, then let's notice something directly below where I've labeled or written sine. So as we already know from work we've done, cosecant is equal to 1 over sine. That's just a familiar definition for us. Well, if that's the case, and we already know that sine is opposite over hypotenuse, then 1 over sine would be the reciprocal of that, which means you just flip those side labels, and therefore cosecant theta would be hypotenuse over opposite. Now, the good news is if we just remember half of these, we will automatically get the others as long as we also remember the way that these are defined, so that, for example, cosecant is 1 over sine. Well, then I really just have to memorize sine, because then I can flip it over to get cosecant. All right, so moving on. Cosine theta is equal to adjacent divided by hypotenuse. And yes, these are the way that those side lengths are labeled in the triangle I've already drawn. I'm just kind of sticking with where I've already labeled theta, and wherever that might be, you can label your sides and get these following ratios. So if cosine is adjacent over hypotenuse, then secant, which is really 1 over cosine, as we already know, would be the reciprocal of the cosine ratio, and therefore hypotenuse over adjacent. But again, the good news is if you remember cosine, then and you also remember that secant is 1 over cosine, then you can just flip the cosine ratio to get the secant ratio. Okay, and thirdly, tangent of theta is going to be equal to opposite over adjacent. And then in the same way, since cotangent is 1 over tangent, we can just flip that ratio upside down to get the trig ratio for cotangent, which will then be adjacent over opposite. All right, so what we're finding is that we have some familiar things to us. That is the definition of cosecant, secant, and cotangent. We've worked with those definitions already. Now we're using them again, but now we're applying them to these trig ratios to really double the amount that we know, right? Because if we know sine, then we know cosecant. If we know cosine, then we know secant, and so on. Now, there's a helpful mnemonic tip that can, I think, make these easier to memorize. A lot of students like this, so I'm going to use this. And it's the phrase SOHCAHTOA. Now, that sounds kind of weird or silly, but it actually really helps. Here's why. The first of those, it's not an actual English word, but it looks like the word so. And that's because it's written S-O-H. Now, why does that make sense? Well, if you think of S, I'm going to color coordinate this so we can hopefully remember it. S representing sine. And we know that sine is defined as opposite over hypotenuse. So if we label those, let me pick some other colors for that. If I label the opposite in a color, I'll pick on a pink color here, then I have sine equals opposite over hypotenuse. But let me also label the hypotenuse a different color. How about a light grayish color? And I'm going to highlight the first letters of these words so that it's obvious, hopefully, that that's what these are representing. So since sine equals opposite over hypotenuse, as we saw in our ratio, then we could say S equals O over H. That is the first letter in each of those words. If you put those together, you get the, little, it's not a real word, but it's a kind of an acronym or a mnemonic device that spells S-O-H, pronounced so. Now, if we do that for all of these, then the next word you can use would be ka. Again, it's not a real word, but it's spelled as C-A-H. And we'll just pick some other colors to represent these. This time I'll pick on purple color for cosine for the C, which means that first letter of the word cosine or cos is our C. And then we'll pick a different color for the next word, which is adjacent. I'll pick on a yellow color for A, representing adjacent. So the first letter in the word adjacent is A. I've highlighted that yellow. That's so we can recognize, that's where the A comes from. And then hypotenuse is also part of this one, but we've already used a light gray for that highlight, so I'll just simply reuse that. Gray for H. So we have ka, C-A-H, represented by, or cosine equals adjacent over hypotenuse. And you'll notice it's helpful if you can spot where things are reused. Now there's one more to go, so we'll go next to tangent. I'll pick on kind of a light blue color for tangent. So tangent is equal to opposite over adjacent as we saw. So we'll use T for tangent. And then we've already used opposite. I'm going to use the same color, this pink color for O. And we've also already used adjacent, which we highlighted in yellow. So I'll use that same color there for adjacent. And so when you put it all together, you get this, kind of word that helps put it all or remember it, which is SOHCAHTOA. Now, you may find other ways to memorize these. If you just look around online, that's fine. You might find one you like better, but SOHCAHTOA is a pretty time-tested method of just remembering these simple ratios. It helps a lot. So we're going to use that for this. All right, next we'll move on to our next item within this topic, which is special triangles. So there are a couple special triangles that are special because they're so commonly used that they're just worth remembering and understanding. And we can create these special triangles from two basic geometric shapes, that is a square and an equilateral triangle. Now you may recall a square is a rectangle where all four sides are equal, and an equilateral triangle is a triangle where all three sides are equal. If we take those basic geometric shapes and slice them up a little bit, we get our special triangles. So let's begin by doing this. If we cut a square from one corner to the opposite corner, so just kind of creating a diagonal directly through the square from corner to corner, as I'm going to do or draw on here to cut it right through or slice it, then you really create two triangles within the square. So let me label one of them, or not label, but just kind of highlight or draw so I can focus on one of those triangles. It's really half of the square, but it's half defined by cutting the square diagonally, not vertically or horizontally, okay? So that gives us a triangle. Now, if that's really inside a square, then we do know that one of those angles already must be a right angle because it's in the corner of the square. So we can mark a right angle, which really creates a right triangle that we're working with here as half of this square. Now, if you think through what's left for the other two triangles, then let's recall you have to have 180 degrees inside a triangle. That's from geometry. And furthermore, these two angles that are remaining must be identical since this is a square and everything is symmetrical. If that's the case, then those must each be 45 degrees. So we're going to label them that way. So inside this square, which we've now cut in half, but we've done so in a diagonal kind of cut, we've created a special triangle which has a right angle and then two 45-degree angles. Now, the way we could label these sides may vary. So, for instance, if you have a triangle, drawn outside to create some kind of landscaping area, then you might have an actual measurement of these sides that you're working with. Okay, those measurements are scalable, like whether we're working with a model that's small on a desk or a large field where we're actually constructing some kind of landscape. And we can change the actual value or measure of those sides, but the scale will go up or down and remain similar in this way. So if each of those side lengths that are across from the 45-degree angle that is kind of meeting at or touching at the right angle of this triangle, if we label each of those side lengths as 1 for a unit measure of 1, then it turns out the hypotenuse, which would be across from the right angle, will always be the square root of 2. Now, why is that the case? Well, think through the Pythagorean theorem for a second. If you think back to what the Pythagorean theorem, which is if you have a right triangle, which we do, then a squared plus b squared equals c squared. That's just the good old Pythagorean theorem applying to a right triangle. Then if that's the case and c is the hypotenuse, which it is in the Pythagorean theorem, then we're looking at 1 squared plus 1 squared equals c squared. And you can find c directly in this way because this means 2 equals c squared if I just add 1 squared plus 1 squared to get 2. And then if I find c by taking the square root of both sides, then turns out c equals the square root of 2, and that's exactly what's labeled in our special triangle. So all I'm trying to show is that these aren't coming out of nowhere. These labels actually do come from the geometry we have of a square or a right triangle. or in the next case, equilateral triangle. So that's where we can label the sides and angles for the special right triangle, known as a 45, 45, 90 triangle, because that's exactly what the measures of those angles are inside of it. Okay, if we move on to the equilateral triangle, which is again a triangle that has all three sides equal in length, then if we cut that triangle right down the middle from top to bottom, that is from, let's say we have the sides oriented on this triangle so that, if you think of the bottom or base of the triangle just kind of being flat on the ground, then directly above it you would have an angle at the very height or peak of the triangle. And if we slice this triangle in half from that top peak angle directly down through the bottom base of the triangle so that it cuts it in half, which it would do because of the symmetry of this triangle, then we get this equilateral triangle, and it does the following. So first of all, if you think of a triangle having three equal angles, which an equilateral triangle does, and you know that there are 180 degrees inside every triangle, then, well, 180 divided by 3 would be 60. Therefore, you're talking about a 60-degree angle inside all the original angles of the equilateral triangle. Well, if we've cut one of those angles in half, I picked on the top one to cut in half, to cut straight down from the top peak of the triangle straight through the bottom base, then you're really cutting that angle in half. Well, half of 60 then would be 30, which means we're creating 30-degree angles that form the total of 60 degrees in the upper angle of the triangle that I've drawn. What we've also then created, if we've dropped this cut down so that it's perpendicular to the base, called a perpendicular bisector, because it cuts it in half and it does so at a perpendicular or right angle, then what we've created are really two triangles that are forming inside of this right triangle. And so if we kind of bring one of those out and just kind of mark it, you're really looking at kind of like side-by-side right triangles in the way that this is drawn. They meet at this kind of bisector cut we've made in the middle, and they also kind of touch at the right angles in the bottom. Then what we're really looking at is a special right triangle here, which has angle measures 30, 60, and 90. So this is sometimes called a 30, 60, 90 triangle. And in the same way, if I were to label some of its sides, we could use the Pythagorean theorem to get other measures of it. One such convenient or familiar way to label these would be that if I take the original base of this triangle that we've now cut in half, and label that bottom side that's now actually half of the original base, if I call that now kind of side of the right triangle length 1, that would mean, well, then the other side of it is also 1, which would then mean the original side of that right triangle, or I'm sorry, equilateral triangle containing both of those would be 2. So if that's the case, then the hypotenuse of this 30, 60, 90 triangle would be 2 if I label one of those legs 1. That's at the bottom, half of the original equilateral triangle side, 1, and then the hypotenuse would be 2. And then if I use the Pythagorean theorem, the vertical side that I've drawn would be the square root of 3. Again, that's just coming from using the Pythagorean theorem to get those side lengths, and which you could double check in any direction of it. Now, let's actually practice using some of our trigonometric ratios that we've defined above on one of these special triangles. So I'm going to pick on the special triangle that we just got out of the equilateral triangle. That is the 30, 60, 90 triangle. And I'm actually going to redraw it so it's a right triangle. I'm even going to spin it around a little bit so it looks oriented slightly differently, just to get us used to that, because the way we spin it doesn't really matter. But the point is it has a right angle, referring to the one we've already used in the diagram, and then it has a 30-degree angle as the smaller one, then it has a 60-degree angle, the larger one, and then also the 90-degree angle. Now, if we label our sides, we know the following. Across from the right angle, as we said above, you will always have the hypotenuse. It's always across from the right angle. So I'm going to label that HYP for hypotenuse. Now, the way we label the other two sides depends entirely on which angle we're going to use. So, for example, in fact, let's just kind of put in an example, pick on a different color here. Let's do an example using our trig ratios. Let's suppose I wanted to find the cosine of 30 degrees. So why does this all, or how does this all fit together? Well, cosine, you'll recall, cosine equals adjacent over hypotenuse. And I know those may still be new or fresh, but you'll eventually remember those by practice here. Cosine is adjacent over hypotenuse. That's the ka of our SOHCAHTOA. So if that's the case, then I'm already kind of picking on the 30 degrees. That's just the one I used. It doesn't really matter which one we use, but I just picked on 30. And according to what that or where that angle is, I will now label the other sides. So if 30 is in one of my corners of the triangle, then across from where that 30-degree angle is, I would have my, well, opposite side. That's opposite or across from the 30-degree angle. That would also mean then next to, or the angle, or the side touching the angle 30 degrees would be the adjacent side. And so we now would have a way to label all three sides: hypotenuse, opposite, and adjacent, but that is all relative to the angle that I've picked and labeled as 30 degrees. So then, if that's the case, and we knew one of those lengths, of course, we would plug it in to find the ratio. We could use the Pythagorean theorem to find the other side. We would just need more information depending on what the problem was. But the whole point I want to make is this: if I pick on a different side length, so let me just pick on a gray color. Let's suppose I wanted to find the sine of 60 degrees, and I was using the exact same diagram. Well, in that case, I would have to label the sides differently, because if I'm picking on 60 degrees, which is the other acute angle, I already picked on 30, but now we're using the 60, then notice the hypotenuse does not change. That's always across from the right angle. But if I'm using 60 degrees, then the side across from that used to be the adjacent, but that was relative to the 30-degree angle I was using. Now if I'm using the 60-degree angle, then the side across from that one would be the opposite. So the way we label the sides depends on which angle we're using. And if I'm using, again, 60 degrees, then the side next to it or touching it would be the adjacent side. And that side, of course, used to be the opposite, related to the other angle, 30 degrees. But if I'm using the one next to the 60, then I call it the adjacent. Okay, what's the big deal here? Well, the point is that opposite and adjacent labels can and will switch depending on which acute angle we're using. So if I'm using the sine of 60 degrees, or if I'm trying to find the sine of 60 degrees, sine is opposite over hypotenuse. That's SO in our little acronym above. And therefore I would, use the opposite and the hypotenuse labels that we have now. But the point is that the opposite label is relative to where the angle I'm using is. So sine of 60 means I use the 60-degree angle to define the opposite, and the adjacent for the whatever label I'm using. So all that to say, the way we label opposite and adjacent depends on the angle we're using, and those can actually switch, but the hypotenuse does not switch because that's always across from the right angle. Okay, let's do some examples that we can use to apply what we've learned so far. The first example says, find the exact values of the 6 trigonometric ratios of the angle theta in the triangle. And then, of course, we're given a triangle diagram, which is a right triangle diagram. Of course, it has to be if we're using our trigonometric ratios. So I'm just going to describe what's going on in this triangle visually so you can have a good idea of what it is. You have a right triangle with a right angle that's kind of oriented near the bottom of the triangle, and then the two sides from that right angle kind of shoot upward to the right and upward to the left. Now, importantly, those two sides are labeled as 3 and 2. We don't have any units here, but they're just labeled with those numerical values, 3 and 2. Now, remember, across from the right angle in any triangle is where we have the hypotenuse. Now in this triangle, that is not labeled. So that's okay. We can figure out a way to find its measure. And then also, one of the acute angles is labeled as theta. Okay, so that's really all we need. We have a right triangle with a right angle, and then one of the other angles labeled as theta. And we are not given the hypotenuse measure, but we are given the two other leg measures. Now, we can label the opposite and the adjacent related to where theta is labeled. Remember, that's what matters because those labels can switch. So if I have theta labeled and then the side across from it is the side labeled 2, which it is, then that's going to be my opposite because it's across from where theta is. Or similarly, the side length 3 that we've already mentioned is next to or touching the angle theta. Therefore, that's going to be the adjacent side. So now we have our opposite, our hypotenuse, and our adjacent all labeled. Theta is labeled as one of our acute angles. We know it's a right triangle given the little square box in the corner of one of the angles. And we're putting this all together. Now, we want to find all 6 trigonometric ratios of theta. So let's think through this carefully. We have sine theta, and the order of these doesn't really matter. We have sine equals opposite over hypotenuse. This is all just coming from what we have above. We have cosine theta equals adjacent over hypotenuse. And then we have tangent theta, and that equals opposite over adjacent. Again, I'm just copying down or reusing what we have above in our definition for these trig ratios. Now, if that's the case, we can actually start plugging in things that we know. So if I want sine of theta, sine is equal to the opposite over hypotenuse. Well, we have that labeled. Opposite is labeled as 2, so I can put that in for the numerator of my trig ratio. What I don't have yet is the hypotenuse, but thanks to Pythagorean theorem, we can find it. So let's bring back the Pythagorean theorem, which says that a squared plus b squared equals c squared. In other words, 3 squared plus 2 squared equals the hypotenuse squared. I'm going to label that for a second as c. So in other words, the theorem says a squared plus b squared equals c squared. I'm going to call that then 2 squared plus 3 squared equals c squared, which means if we solve for c here, we'll have 9 plus 4 equals c squared, which means 13 equals c squared. If we take the square root of both sides of our equation, then we should be able to solve for c, which gives us that c equals the square root of 13. You may be used to taking or using a plus or minus in front of a square root, which algebraically is proper, but in the case of an actual side length, we don't use negatives for it, so you can ignore the plus or minus. Okay, so this means that c, the hypotenuse length, equals square root of 13. If that's the case, then I just plug that in where we see the hypotenuse label in our trig ratio. Now let's also remember, as we've defined above, that you have reciprocals for the rest of these trig ratios. So for example, since cosecant is really just 1 over sine, then if you know sine, you know cosecant. So I can say cosecant, I'll abbreviate that, CSC, cosecant theta, same theta here, is 1 over sine theta, but we just found that sine theta is 2 over root 13, which means 1 over that would be the reciprocal, root 13 over 2. So in other words, if you find one, you can find the other just by using the reciprocal. So we now know sine and cosecant. If we know cosine, then we can also find secant. I'm just going to fit these in here. So secant is equal to 1 over cosine, and since we already know cosine, we should be able to find both. So let's finish this. Cosine is adjacent over hypotenuse. Well, we've labeled the adjacent side being 3, and the hypotenuse we just found to be square root of 13, thanks to Pythagorean theorem. So the cosine of theta is 3 over the square root of 13. Well, if secant is 1 over cosine, then we simply flip that over to say square root of 13 over 3 for secant. And now we have them both. Okay, so similarly, let's finish this up. Tangent is opposite over adjacent, and our opposite is labeled as 2, and our adjacent is labeled as 3. So tangent of theta is opposite over adjacent, which is 2 over 3, labeled the way they are in our diagram there. But then, if that's the case, then cotangent theta is 1 over tangent theta, which is simply the reciprocal, so that would be, well, 3 over 2. And now we have both of those as well. So as you can see, there's really, it all just kind of comes together once we label the triangle correctly according to where theta is. And remember, your opposite and your adjacent can only be labeled properly according to where theta is. But your hypotenuse is always across from the right angle. And so once you get those sides labeled correctly, and in this case we were given 2 measures of the sides, we were given the adjacent and the opposite, then we just use Pythagorean theorem to find the missing side. That will always work. Whatever side's missing, you should be able to find if you know 2 of the other sides, and then plug them all into the ratios according to the way they are. Now, the one thing you might also see done that I want to reference is you might see these ratios rationalized. So let me just kind of do this as an example with the first one. For sine theta, we got 2 over the square root of 13. If I rationalize this, from algebra you may recall, that means you would multiply by the square root of 13 over the square root of 13. It just makes it so that there is no square root in the denominator, because then that would reveal on top 2 root 13 over, on the bottom you'd have square root of 13 times square root of 13, which is really just 13. So you might see it written in this way. It's called rationalized. And that's something you might see if you're like checking an answer in a textbook, or they may want an answer put in for a homework system online like that. It's just a simple rationalization step where you multiply by the root of the denominator in order to cancel out the square root and just reveal the whole number inside of it. So you can do that with all these that have roots in the denominators. In this case, there are only a couple of them, but you might see that done here or there. I just wanted to reference that. Okay, let's try a couple more examples, but these are set up a little bit differently. So the next says, find the side labeled x, if needed, round to 5 decimal places. Okay, and then we have a triangular diagram given in the following way. It's a right triangle, so it's got a right angle labeled. It has a 30-degree angle labeled in one of the other angles. And then across from the right triangle, across from the right angle, which of course is the hypotenuse, that's labeled as 25. And then across from the 30-degree angle, you see the label or the variable x. Our goal is to figure out what x is, find the measure of that side. So let's think through this carefully. If I know the 30-degree angle is labeled where it is, then the side across from that angle is automatically the opposite side. So let me just kind of label that as the opposite, right? That helps us know which ratio might be appropriate to use here. The side across from the right angle we've already labeled as the hypotenuse. And what this really means is we're trying to find x, which is labeled on the opposite side. Now, notice there's nothing labeled on the other side. We know that that would be the adjacent side because that's the only one left. But we're not given that side length, and it's not missing to find with a variable x. So we actually don't even care about that side length. We're going to ignore it for now. What we need is a trig ratio that will involve both the side we know, that is the 25, and the side that we want to know, which is the x. That determines which trig ratio we're going to use. Which side do we know, and which side do we want to know? Well, it turns out we know the hypotenuse, so we want to use something with an h in it, but we also want to know the opposite, which has the o in it. So what we're doing is looking for a trig ratio that has an o and an h, and I'm referring to the SOHCAHTOA. Well, that only leaves one option. That would be sine. So we could say sine of 30 degrees, that's our angle, is opposite, that's x, over hypotenuse, that's 25. So again, this is just using the SOH from our SOHCAHTOA. And we knew which one to use based on the information we had. Only one of them makes sense to include both the side that we know and want to know, which again is the hypotenuse and the opposite for this one. At this point, we're just going to solve for x, which we can do algebraically by multiplying both sides by 25. So that the 25s will cancel on one side of the equation. We had x over 25. We're multiplying that by 25, so those cancel. But then the other side had the sine 30. We're going to multiply that by 25 as well. We're ultimately trying to solve for x here to get this value. So we're going to do that now with just by computing it. X equals, as we've already seen algebraically here, 25 times the sine of 30 degrees. Now in this case, it said to round to 5 decimal places if needed. So let's think through this carefully and then use our calculator for this value. Now I'm going to demonstrate this on the graphing calculator, but actually, since 30 degrees is one of our special triangle angles that we've already defined above, you could get away with finding an exact value for it even without the calculator. So in those cases, in some cases we will just use the special triangle value, but I want to demonstrate the calculator here for this one, since it's also a nice one. So we can do this in the following way. I'm going to turn on my calculator. Since we're working with degrees, this is given as 30 degrees, we have to be in degree mode. So I'm going to click on the mode button in the upper left kind of area of the calculator. You'll notice when you click mode, a few lines down, you see two options. One of them says radian and one says degree. Well, both of those are familiar words to us by now, but by default, radian is selected, so we need to make sure we go over to degree and hit enter on that. Otherwise, it will not give us the correct result. So I'm going to hit enter to get degree mode. Then I'm going to quit by hitting second and then the quit or mode button. Now that I'm in degree mode, I'm simply going to type in what we know we need, which is 25 times the sine of 30. Now the way we can type this in is by doing 25 and then just putting sine directly next to it. The calculator will assume that should be multiplication. And then I'm typing in 30 because it's in degree mode, and that's what I want, 30 degrees. Then I'll close my parentheses and hit enter, and it's going to give me a value of 12.5. Now if we go back and write that in, notice that does not need to be rounded, and that's because these numbers worked out nicely with our special triangle numbers above. Sometimes if they're nasty numbers, which you get when using some of the roots, the square roots, you will get a repeating decimal, and that's why they're saying to round to 5 decimal places if needed. But this one turns out nice, 12.5 it is. Let's try our next example to the right, number 3. This one is given as a right triangle, and directly across from the right triangle, or the right angle, is of course the hypotenuse, and that's labeled as 13 for this triangle. One of the acute angles, also inside the triangle, is labeled as 60 degrees. And then across from that angle, you see, in this case, the value x, or the variable x that we're trying to find. So now let's label this carefully. We know across from the right angle is the hypotenuse. We already have that labeled. We're working with the 60-degree angle as given. Across from that angle, then, would be the opposite, since it's across from the 60-degree angle. That means the side that's next to the 60-degree angle would be the adjacent side, but it's not labeled with a known side or a variable, which means we don't even need it. We're not even going to work with it. We're only working with the side we know and the side we want to know, which of course, in this case, the 13 is the hypotenuse and the opposite is the x. So we need a trig ratio that involves both the opposite and the hypotenuse, which again would involve the options you have above. We could use sine because it involves both the opposite and the hypotenuse. So we'll say in this case the sine of 60 degrees, that's our angle we're working with now that was given. Sine is opposite, that's x, over hypotenuse, that's 13, again just the way it was labeled, and we can solve for x just like we did in the previous problem by multiplying by 13 on both sides. So if I multiply both sides by 13, the 13's cancel on one of the sides, leaving us with x equals, and then we have 13 sine of 60 degrees. So let's bust out the calculator and try this one again on it, since again we have degrees, but we're in degree mode, so it should work out okay. But let's see what happens. If I plug this in as given, so 13 sine of 60, I'm going to do 13 sine, this time I'm putting in 60 degrees, close parentheses. If I hit enter, this time we're getting kind of a nastier looking decimal. It's 11.258333025. It's kind of a long decimal, which means this probably involves one of the radical or root values in one of the special triangles above. So that's okay, but let's practice it now two ways. So it said to round to 5 decimal places, which we can do simply by using the value we have and rounding it accordingly. So that would be 11.25833 rounded to 5 decimal places. That's acceptable based on the way that this problem was given. It said to round it if needed, so that would be an acceptable answer. But I also wanted to explain how you can get an exact answer, which would be a non-decimal or non-rounded answer. Could be a decimal, but just not rounded. In that case, we could use the special triangle ratios we knew above. So we're looking for ultimately the sine of 60 degrees. That's what we're trying to calculate. Well, if you go back up to the special triangles we did, we have a 30, 60, 90 triangle. And actually, the way it's labeled, we could find the sine of 60. We started with it earlier, but we didn't finish it, so I'm going to do that now. The sine of 60 degrees would be, we already said opposite over hypotenuse. Well, if I pick on where 60 degrees is in my special triangle, the side opposite of it would be square root of 3. And the hypotenuse across from where the right angle would be in that special triangle would be 2. So we'd be looking at square root of 3 over 2. That is the sine of 60. So if I go back down and plug that in for what I'm doing here, then what I'm really working with in this example is, instead of 13 times the sine of 60, I could say that's really 13 times what we just figured out that was, which is the square root of 3 over 2. This is an exact answer because there will be no rounded decimal in it. And in fact, it doesn't simplify much beyond that. You could just write this as 13 square root of 3 all over 2. That would be your exact answer form of this same value. Okay, so let's get through maybe a couple more examples in this. The next one is given as a right triangle, and the angle provided inside of it, besides the right angle, is the acute angle 36 degrees. And then across from the 36 degree angle, we have the label for 12. Of course, that would be opposite. So the opposite sides of measure 12. And then the side length that's next to it, but not the hypotenuse, would be the adjacent side. That one is labeled as x, which is what we want to find. So this time we're going to set it up in the following way. We know the opposite and we need to know the adjacent, which means we need a trig ratio that involves both of those. So if you look up at our options for SOHCAHTOA, which option involves O and A for opposite and adjacent, turns out it's tangent. So we'll say the tangent of 36 equals the opposite, which is 12, over the adjacent, which is x. Now we have to do a little bit of algebra in order to solve for x on this one. You could think of tangent 36 as tangent 36 over 1, and then you could simply cross multiply these. This would give you x times the tangent of 36 degrees on one diagonal equals 12 times 1 on the other diagonal. So by cross multiplication, we get x tan 36 equals 12. And of course, I could solve for x by dividing by tangent of 36 on both sides, which would give me 12 over the tangent of 36 degrees. And so now we want to compute this value, which we'll go ahead and do on a calculator. Now notice this degree we were given, the 36 degree angle, this is not one of our special triangle angles. So if that's the case, you cannot use a special triangle ratio for an exact answer. So we'll just go to the calculator and plug this in as we see it. We want 12 divided by the tangent, so we'll use the tan button on our calculator, of 36 degrees. Again, we have to make sure we're in degree mode, but we already took care of that. So I'm going to compute this to get the value 16.51658. or that is rounded to 5 decimal places, we could use that. So 16.51658. We're not going to get any better than that as an exact answer because 36 degrees is not one of our special triangle degree angles. All right, let's move on to another example. This next one says, sketch a triangle that has acute angle theta, given that sine of theta equals 3/5, and find the other 5 trigonometric ratios of theta. Okay, so all we know is that we have a triangle with this angle, and we're going to have to assume that it's a right triangle if we're going to use our trig ratios. So what we're going to do is just draw any old right triangle. We're going for accuracy, not artistry, so try to just draw a right triangle that's easy to read or follow. You have to label a right angle in it. Doesn't matter which way you orient or spin it around, but I'm going to label a right angle in a triangle. And then it has acute angle theta. Well, again, we can just label that as one of the other angles. It doesn't matter which one's which, or which of those other 2 angles you label. What we know is that the sine of theta is given as 3/5. Okay, so now think about this. Across from the right angle is always the hypotenuse, so we can label our hypotenuse as soon as we label our right angle. And then as soon as we label theta, then across from that label, we have the opposite. So that works no matter which way you've labeled or oriented. If you label theta as the other angle, then the opposite would switch, right? So that's we got to label something like that. If we know that sine theta is opposite over hypotenuse, which we know from our trig ratios defined above, and we know that that's given as 3/5, then we know the opposite could be labeled as 3, and the hypotenuse could be labeled as 5, just the way those are given. Well, if that's the case, and we're trying to find all the other trig ratios, we need the missing side. But thankfully, from Pythagorean theorem, we should be able to find it. So, for example, we know if I call that missing side x for the moment, then I know that x squared plus 3 squared would equal 5 squared. That's just using the Pythagorean theorem, which we reviewed above, the Pythagorean theorem, which means that x squared plus 9 equals 25, which means x squared, if I subtract 9 from both sides, I get x squared equals 16, which means x must be 4. Which means that side length at the bottom of our triangle, which I've labeled at the bottom, it's actually the adjacent side because it's next to the theta angle, and it's the only one left. That's our adjacent. That must be 4. Okay, if we know that, then we can find anything else we need. So we want to find the other 5 ratios. Well, sine is 3/5. Let's see, cosine, all we're going to use our trig ratios. Cosine is adjacent over hypotenuse. Remember, ka for SOHCAHTOA? Well, adjacent, the way it's labeled here, will be the one we just found. That's 4 over hypotenuse, which we had already known as 5. So we now have cosine, we have sine. We could find tangent theta. Tangent is opposite over adjacent for TOA. Well, again, opposite is labeled as 3. Adjacent is labeled as 4, so 3/4. And we could find the others as well. So let's see, secant theta, secant is 1 over cosine, so that would just be the reciprocal of cosine, so 5/4. Cosecant is 1 over sine, so sine is 3/5, which means the reciprocal would be 5/3 for cosecant, just using the reciprocal. And then lastly, cotangent theta would be the reciprocal of tangent. We already know tangent is 3/4, so 4/3 for cotangent. You'll notice then, as long as you know the basics, you can kind of just use all the reciprocals and Pythagorean theorem to find everything else you might need for an example like this. Okay, last but not least, we want to evaluate the expression without using a calculator. Okay, what does that mean? Well, the expression reads sine 30 cosine 60 plus sine 60 cosine 30. Well, if we're not going to use a calculator, we have to find a way to know what all of those values would be, right? Sine of 30 or cosine of 60 or sine of 60 or cosine of 30. Well, you may recall above we have these special right triangles. Can you think of one that involves a 30 and a 60-degree angle? Yes, we do have one. It's called a 30, 60, 90 triangle. So let's draw one of those. If we draw that and label the sides as we have them above, you'll recall we have 1, 2, and square root of 3 to label, where the 2 is the hypotenuse across from the right angle, and then the 1 is the shortest side, and the square root of 3 is the other side in between those. So we have that just from our special triangle. I'm going to say that above, see above. We already kind of discussed we have a 45, 45, 90 and then a 30, 60, 90. Well, since these expressions all use 30 and 60, we should be able to use the 30, 60, 90 degree triangle, special triangle, to find what we need. Now I want to find several things. So for example, I want to find the sine of 30 degrees. That's one of my values in my expression here. And if that's the case, sine of 30, notice 30 is labeled in one of the angles. Sine is opposite over hypotenuse. Well, the hypotenuse is the same no matter what, across from the right triangle. That's always the length 2 in the 30, 60, 90 triangle. So if I want the sine of 30, I want to go opposite 30, that would be where the 1 is, over the hypotenuse, which is 2. So sine of 30 is 1/2. That's just using the SOH, ratio, trig ratio. Sine is opposite over hypotenuse, but I'm anchoring it with the 30-degree angle wherever that's labeled. So opposite of it is 1, and hypotenuse, of course, is 2. So we're using those labels and things we've developed above in order to simply get that ratio or that value for sine of 30 degrees. Well, we're going to do the same kind of thing for all these other. That takes care of the sine of 30. I also need the cosine of 60. So similarly, I'm going to go cosine of 60 degrees equals, now 60 degrees is one of our angles labeled. Cosine, remember C-A-H, ka, for so ka, toa. Cosine is adjacent. So now I'm talking adjacent relative to the 60-degree angle, because that's the one we're using as the input here. So 60 degrees is marked in our triangle diagram. Adjacent to that would be the 1 length. So there's cosine is adjacent over hypotenuse, which would be 1 over 2. All right, so far we have sine of 30 and cosine of 60. We also need the sine of 60. So we've already used sine as opposite over hypotenuse, but now we're using it with a different angle. The first time it was 30 degrees, now we're working with 60. So if you go to the 60-degree corner, opposite of that would be root 3. That's looking across from where that 60-degree angle is. And then the hypotenuse is 2, so we're looking at square root of 3 over 2 for the sine of 60. And then lastly, the cosine of 30. Again, just mark that down. Cosine is adjacent over hypotenuse. So we're looking now at the 30-degree angle. The adjacent side to that is root 3. And the hypotenuse is still 2, always is, there in this diagram. And so we have square root of 3 over 2 for the cosine of 30. So this is just a lot of good practice with the trig ratios. If you put this all together, then we're looking for sine of 30, which we said was 1/2, times the cosine of 60, which we said was also 1/2, plus, this is just the expression given originally here, sine of 60, which we just found to be root 3 over 2, times the cosine of 30, which is also root 3 over 2. All we got to do is put this all together, which gives us 1/4 plus 3/4, which of course is just 1.